Alright, today we're going to do the Grignard reaction. Now we're going to start the reaction. It's going to need some time to go. It's going to be like a 30-minute reflux, and we'll talk about what a reflux is while it's doing it. And so first we're going to start the reaction, then I'm going to go through the reaction mechanisms on the board and how to find the theoretical yield and the limiting reagent. Alright, so first we're going to need, if you're following in your Grignard reaction, we're going to need some magnesium. So I weighed out 1.2090 grams of magnesium. That's 1.2090. And I'm putting it in a 250 ml flask. Come out. All right. So I use the stirring rod we're going to use later, and I will make sure that I get all the magnesium in there without spilling any. All right. So all the magnesium is now in the flask. Alright, and so we're going to need some ether, and we're going to use diethyl ether. It is absolute, which means it has 0 water in it. You can buy ether, diethyl ether. If somebody says they want ether, they want diethyl ether. There's, of course, many ethers. But if somebody just says, I want ether, they want diethyl ether. All Grignards must have ether as a solvent. It doesn't have to be diethyl ether, but it has to be an ether for the solvent of a Grignard. All right, and so I just have my ether in there with my, and I put in 38.5 mils of ether. That doesn't really matter, that's just the solvent. And now I'm going to put in 5.5 grams of bromobenzene. And this will start the reaction. Now, this reaction will take a while to start. So, in order to wait for it to go, which it will go eventually, to form the Grignard reagent that I will go through on the board, what we're going to do is we're going to need to add a catalyst. And so, iodine is a catalyst for the Grignard reaction. So, it is a catalytic amount of iodine. You do not have to weigh it. It is a catalyst. You're putting in a catalytic amount. So I'm just going to get some on the tip. All right. Let's see, I need a better scoop. Yep, here's the best scooper. All right. So I'm going to get a scoop of iodine. I'm going to put it in there. So iodine is a purple color, so you get this reddish color. Alright, so the key here is we have to make sure that this reaction starts. Alright, and the boiling point of ether is around 38 to 40 degrees Celsius. You can look that up exactly. So my hand is warm enough to boil this solution. What we want is we want to make sure that this is boiling because of the exothermic reaction, not because we are holding on to it. All right, and so for the magnesium, which gets a coating of oxide on it, in order to make sure that it is has a nice coating, or to get the coating removed so it's reacting with the magnesium, we're going to use a Grignard starter. All right, so this is just a stirring rod that I flattened the end, and I'm going to push the magnesium on the bottom of this flask to expose some fresh magnesium without the coating of the oxide, and that will then react with the bromobenzene. And if this is working, it's going to take a while to warm up it's very cold in this room today. It's going to take a long time to warm up the ether to boiling. Right now it's at about 20 degrees Celsius. We have to warm it to 40, and we have 38.5 mils in there. So the reaction is going to have to go a while before we get that amount of heat to boil the ether. All right, so what's going to happen prior to the boiling, and the way we're going to know that the reaction is starting, not only is the iodine a catalyst, it also is an indicator of the reaction that is starting. You're going to see a color change. Right now you have a dark reddish purple brown color, and you're going to see it lighten up. So it should, if the reaction is starting, you're going to see this color lighten up, and then soon after it changes the colors, it will then begin to boil. Now once it starts boiling, I said we're going to reflux it. All right, once this changes colors, I will note that as well. All right, so behind me and to this side, I have this setup right here. All right, and so the condenser is straight up and down. So when the condenser is straight up and down, you're going to do what is called a reflux. So a reflux is we're going to boil this. It's going to vaporize, and then I have water going through here. Turn on water a little bit more. Whoa, not that much more. All right. So we have water going through here. I can show the water coming out. All right. So the water is coming out. So it's going in the bottom and out the top. So this is full of cold water. And so when it goes up, it sees the cold water. Or it gets cooled by the cold water, and then it condenses back into a liquid, and then it drifts back down in to your flask. So you are boiling it, but you are not losing any of your solvent. All right, and so that is a reflux. So reflux is boiling without you losing your solvent. If you just boil water, eventually your water is gone, and now you're just heating it. So a reflux means you can boil it forever. It just keeps on boiling. You don't lose any of your solvent to evaporation because, well, you're going to lose a little bit because the top is open. But you're not going to lose very much. You can boil for a very, very, very long time before you're going to lose any volume. Okay, let's see. All right, I'm looking at the bottom to see if there's any bubbles being formed. I'm noticing some color change. It's more of a opaque look. Okay, let's see over here. Something's going on down there, and so it's very, very opaque looking. Looks like it's forming a solid, but it's just starting the reaction right now. And so it is starting to boil. Usually it changes colors, so maybe it's going to change colors here right in front of our eyes. And so it is boiling. So the reaction has started. So the Grignard reaction has started, and this is going to boil itself. It's very exothermic. I'm not going to have to heat it. It's going to boil and do a reflux all by itself without any external heating. All right. So hopefully you can see the reaction. I'm holding the top on purpose. It is not me heating this up. It is reacting as we speak. You can see on the bottom you've got your magnesium. That's going to do reacting. It is boiling inside of there. And you can see that the color is changing. It is more of an orange, yellowish color instead of the dark red color. And so again, I can see it boiling. I know the reaction's going. I see the color change, also an indicator that the reaction is going. And so now it is more of a yellow color. All right, so I have the solvent front. This is getting very hot, and now we're losing some of our ether. Again, I put in plenty of ether. We can lose a little to evaporation. Ether is just the solvent. All right, and so I'm going to hook this up, and it is going to boil on its own. So obviously a color change here. and it is going to boil on its own for about 30 minutes is the average amount of time that it boils by itself, again while it's doing its thing. And now it's turning a whitish color. Alright, so I think it is going quite well. I don't think I need to smash any more of the magnesium. Once the reaction gets going, it is good to go. You shouldn't have to do anything else. And it will boil for about a half hour. So it's looking really good right now. I'm going to go ahead and hook it up. Alright, and so we could hook it up just for the Claisen the reflux, but we're going to use a setup that we're going to use because we are going to then we're going to need to add another liquid, and so we're going to do a Claisen addition. And so this is a Claisen adapter, and so we're going to use that now so I don't have to change to it later. Okay. And you make sure that the stopcock is closed. All secure. All right, so on here your stopcock is closed so that the vapors are all throughout here, but the only escape route is up your condenser tube. All right, and so the solvent, you can see now, hopefully I'll bring it up here, but it's going up, it is condensing in the condenser, and it is dripping back down. And so I have to make sure that the water is flowing through. Alright, the water is flowing through. Alright, so this is going to go, and I will give you a closer look at this. This is going to go again for 30 minutes. And so the heater is off. It is completely off. There is no heat on. This is boiling due to the exothermic reaction. The condenser, you see the drips right there. The vapors are going up into here, and then they are condensing because of the cold water that's up in here and dripping back down into the reaction vessel. All right, and that's just showing over there that the water is flowing quite nicely through the condenser, cooling it. All right, and so this is going to boil for about 30 minutes or so. It's probably been going for at least 5 or maybe 10, so we probably have another 20 minutes or so before this is going to stop boiling, and then we can continue with our next step. All right, now the Grignard we're going to have on the board here. I'm going to show the reactions that are going on. Okay, so we have the Grignard synthesis of triphenylmethanol. So in step 1, step A, I'll say part A, what we're doing right now is the synthesis of your Grignard. In this case, the Grignard is the phenyl magnesium bromide. And so as I stated, we take bromobenzene and we took magnesium. We took 5.5 mils of bromobenzene. We took 1.2090 grams of magnesium solid. And we are forming this Grignard. This is the phenyl magnesium bromide. The benzene ring as a group is a phenyl group, so that's phenyl magnesium bromide. All right, if you look at the periodic table, magnesium is in the +2 column, bromine, the halides, are in the -1 column. So what this is a phenyl with a negative charge. This is a very, very, very basic, very nucleophilic phenyl reagent, your Grignard reagent. So this is a source of carbon minus. You can make a Grignard out of any alkyl halide, any aryl halide. Any halide can react with magnesium in the presence of ether to give a Grignard. All right, I didn't put iodine over the arrow. Iodine should be put over the arrow. Iodine was used in this step as a catalyst. But that's it for part A. That's the whole reaction. Now we're going to need 2 equivalents or 2 moles of our phenyl magnesium bromide, and so I multiplied everything by 2. So it was balanced as a 1 we are going to need 2 of these phenyl magnesium bromides. And so you should write it in your lab write-up with the coefficients of 2 going all the way across. All right, and that's it. That's the only reaction that we're going to do for part A. Now, once we let this go and we have our phenyl magnesium bromide, we are not going to weigh it at that time. We're going to get an overall yield. We're not going to get a yield for each part. So then we're going to go to part B. Now, part A was just 1 step. That was it. Part B is 3 steps. So you're going to have to balance each step and give the overall reaction for part B. There's 3 parts in this reaction. So in part B, the synthesis of the trimethyl methoxide, trimethyl, I should say triphenyl. Triphenyl. All right, let me change that. So that should say triphenyl methoxide. All right, so here's the reaction. Here is step 1. Our Grignard, the phenyl magnesium bromide, reacts with 1 equivalent of our methyl benzoate. So that is methyl benzoate. We haven't added that yet. We're just doing part A. We're going to add that next. That's why I added the addition funnel so that we can add our methyl benzoate. All right, so anytime you have a Grignard, your magnesium bromide, if you're making it, if you're using it, you always have to have ether. In order, when you have a Grignard reagent, whether you're reacting it or you're producing it, ether is always a part of that reaction. So again, ether, and in the case that we're using, it is diethyl ether that we're using. All right, and so there's the mechanism. The negative carbon, the negative phenyl, attacks the positive carbon of a carbonyl. It is positive because oxygen is very electronegative, and so that gives the carbon a delta positive charge. And so that negative carbon attacks the delta positive carbon of a carbonyl, of a C double bond O, and that is going to put now 2 phenols, because we already had 1. Now we have 2 phenyl groups, an O minus and the OCH3. Now the negative oxygen, the electron pairs come down, reform the double bond, and kick out the OCH3. For normal reactions, OCH3 is a terrible leaving group. For the Grignard, which is extremely basic, extremely nucleophilic, the OCH3 is actually a good leaving group in a Grignard reaction. All right, and so I also put the magnesium bromide, MgBr, but it's not magnesium bromide. It is the MgBr plus to go with that O minus. Again, you're going to have to balance every single step. And so the Mg is +2, the Br is -1, the MgBr overall is a plus. And so you have your negative carbon and your MgBr plus. All right, so once you have reformed the carbonyl, you have a ketone. You have your diphenyl ketone. All right, so now a Grignards react with C double bond O's, because C double bond O, the oxygen is very electronegative. You have a delta positive carbon. And so that's why we had to make 2 of our phenyl magnesium bromides. The second phenyl magnesium bromide attacks the ketone and pushes the electrons to the delta, to the highly electronegative oxygen. And so this is then your final product for part B, and that is your triphenyl methoxide. All right, and again, it is a negative, and you have your MgBr plus because you're going to have to balance step 1, balance step 2, balance step 3, and give the overall reaction for part B. All right, now once that reaction is done, we're going to go to part C. And in part C, it's going to say to take this product of part B and react it with sulfuric acid. And so this is simply a protonation. And so you have your triphenyl methoxide, the negative oxygen attacks the hydrogen on your sulfuric acid, to form your product. The product for this is the triphenylmethanol. So there is your product. And then for this reaction, so part C again is a one step. So that's it. You don't have to do anything. I balanced everything for you. The only thing you're going to have to change is part B. You're going to have to give step 1, step 2, step 3, and the overall reaction of part B. Part A, write down just as I wrote. Part C, write down just as I wrote. All right. So now I have the coefficients that we have to worry about, and the coefficients are these. For this reaction, we need 2 moles of bromobenzene, 2 moles of magnesium. We need 1 mole of methyl benzoate, and that will produce 1 mole of our product. All right, so I'm going to show you how you're going to calculate your theoretical yield. I'm not going to do it, but I am going to show you how to do it. So to calculate the theoretical yield, you have to take your 3 reactants. We do not need to do the catalyst. We didn't even weigh out the catalyst, so catalyst is not going to be an issue. All right, so with our bromobenzene, we used 5.5 milliliters of our bromobenzene. So once you have your table of constants, you will have the density. You multiply it by the density to give you grams. The milliliters will cancel. Then you have on your sheet the molar mass of bromobenzene. So you will have to divide by the molar mass in order for the grams to cancel and give you moles. And then from what I showed you just before, we see that 2 moles of your bromobenzene are required to produce 1 mole of your product, which is your triphenylmethanol. And then you will need your molar mass of the triphenylmethanol, multiply by that, and now you have your mass of product. All right, you're going to do the same or similar thing with the magnesium, except magnesium we didn't use a volume, we used a mass. So we used the 1.2090. So we can put that in there, 2090. So it said to weigh out 1.2 grams. The actual amount that I weighed out was 1.2090 grams. All right, and then you divide by the molar mass of magnesium to get moles of magnesium. Then, again from before, the mole ratios, 2 moles of magnesium produced 1 mole of product. And then you have the molar mass of your product, multiply by the molar mass of your product, you then will have the mass of product produced from that magnesium. Then you take your methyl benzoate and you do your 3.2 mils. We still have to add that, we haven't done that yet. You will have the density of your methyl benzoate. And so you then multiply by the density. For the milliliters to cancel, you get grams. Then you divide by the molar mass to get the moles, and then you have your mole ratio. For your methyl benzoate, it is a 1-to-1 mole ratio. 1 mole of the methyl benzoate produced 1 mole of your triphenylmethanol, and then the molar mass of your product, and then you will have your mass of product that you can produce from each one of these 3 reactants. And remember, the lowest number that you get in this calculation, the lowest is the theoretical yield. And whichever one gives you that lowest value and the theoretical yield, that is your limiting reagent. All right, and so that is what we're doing for the write-up of the Grignard. So let's go see how our reaction is looking. All right, so here is our reaction vessel. All right, so it is still boiling, but it is not boiling at a rate where you're getting any kind of reflux going. It is not boiling enough to take the vapors all the way up and back down. It is not dripping anymore. All right, and so we are looking to be finished with this part of the reaction. So there's no more dripping. You can see the solvent front. It is going up the flask, and then it is just cooling from the air because this reaction is not going very fast, so it's not heating it up very much. And so the coolness of the air in the room is enough to condense it. It's not going up to the condenser. All right, so we're going to get ready to add our next reactant, which is our methyl benzoate. All right, so I'm going to get the methyl benzoate ready, and we're going to then add it dropwise through our funnel. All right. Okay, so we have our methyl benzoate, 3.2 mils. Diethyl ether, diethyl ether is 3.2 mils and 12.5 mils diethyl ether. All right, so we're going to put into our addition funnel 3.2 mils of methyl benzoate, and the stopcock is closed. All right, and then we're going to add our ether, 12.5 mils of ether, and then I will add that by putting it into this graduated cylinder with the 3.2 mils. Make sure that all of that 3.2 mils goes into our funnel. All right. And so right now there is little to no boiling at all going on here. All right, and so let's see, we are going to cool this. I got an ice bath over here, so we will cool this down a little bit. All right. All right, so we are cooling down our reaction so that we can then add this. When you add two things for a reaction to begin, you want that to be at a low temperature so that you don't have too much energy to form a bunch of different products. You want to form just the one product you're looking for. So the higher the temperature, it leads to a lot of side products that we do not want. We want the one product that is supposed to be formed. So we cool it down, we add our stuff slowly, and we get the correct product with a higher purity. Alright, so I'll let this cool off a little more. I might add some more water in there, maybe a little bit more ice. Alright, so that is good. So now I'm going to add slowly. So I have the top on. That would not work for adding. Alright, so stopcock off so that we can add this slowly. So we're adding it dropwise. Let me get this camera up here close. This is interesting colors here. And so it's turning a dark red. All right, so, and as it hits there, it is turning white. And so it's dripping in. I got it at a pretty good drip rate here. All right, so again, I'm not really worried about the yield. So I don't mind if there's a little less yield than usual. But if you wanted it to be a higher yield, you would want it to make sure you probably give it more time for cooling and drip it in there a little bit slower. All right, but it is doing exactly what it's supposed to be doing, and it is looking great. So once it has all been added, I will swirl it around a bit, make sure all the reaction is complete. But this reaction is very, very fast. This is a Grignard reaction, which is going to react very fast, and that's why we cooled it down. All right. So this is a very colorful reaction experiment as well. Alright, so we got, what do we have, whatever, about 15 mils to add in there total. So this will take a little bit. I can shake it up, make sure it's reacting. It's in the ice bath, so it should be plenty cold for this reaction, so we should get good yield. Alright, so let's see what we're going to do next. So after we add this, it says to let it set for a long period of time. We are not going to let it set for a long period of time. We are going to go on with the next step. Alright. So the bromomagnesium derivative of the alcohol, the product is the triphenylmethoxide. It is a white solid. So that white solid being formed, that was a good sign. I don't know if you can see the color now. So instead of red, we're pink. So I can bring you over and show you that. And we have added all of it. And so after adding all of it, you can maybe see that that is pink. So that is a pink color, not a whole lot different than the red it was before. But all right, so we will get ready for the next step, which is the protonation. All right. So it says let it stand for 15 minutes, and preparing all this stuff might take us 15 minutes. All right, so what we're going to do is we're going to take and we're going to pour this into a mixture of ice, water, and sulfuric acid. All right. And We're going to add that to a, let's add it to a large beaker. Go with, let's put it in a beaker. All right, so eventually we're going to put it into a separatory funnel. So we have to take this apart. We're going to use a separatory funnel soon. All right, turn the water off. Don't need that anymore. All right, so we have our pink product here, and again, I'm going to swirl it, make sure that, and it is quite cold, and so the reaction takes a little longer when it's cold, but again, this is a very fast reaction. So I'm going to swirl that occasionally as I'm preparing for the next step. All right, I need my sulfuric acid, which is over here. All right, so we have our ice water, we have our acid, and you always add acid to water, so we add the acid to the ice water. And then adding sulfuric acid to water is very exothermic, that's why we wanted it to be very, very cold. All right, so now so pour the contents of the flask into this acid. All right, and so we can, to make sure it all comes out, we can go back and forth with the reaction. If there's any solids in here that are not going to come out on the first swipe, we can pour it back in and back out and back in and back out, make sure everything is where it needs to be. All right. All right, so this was supposed to sit longer than this, but we're going to go with it. And so here is my acid, my cold acid solution. All right, so you're going to get bubbling, and that is because the acid is reacting with the unreacted magnesium. So as I poured it in, I saw that there was unreacted magnesium. And so the magnesium is reacting with the sulfuric acid, producing hydrogen gas. And the other thing I didn't mention is with ether and now with hydrogen gas, we don't want any flames. And so any heating that we would have done, we haven't done any, but that is what we would use the hot plate for. We are not going to use anything but the hot plate. And so the reaction going on in here is, well, we protonated our product. We protonated the triphenyl methoxide into the triphenylmethanol, so that is what the acid did. But also the acid is reacting with the magnesium, producing hydrogen gas. All right, and so that's an exothermic reaction. And so this is, it's, I don't know, maybe a little above room temperature. It's a nice little hand warmer because it is cold in here. All right, so with this reaction, you may be also seeing, and you can hear it, that is definitely a reaction generating hydrogen, but it's also exothermic, and so at some point, if you see bubbles, it could just be that the heat is high enough to boil the ether. All right, so we will let that do its thing. All right, and so then we're going to add 3 mils of 20% sodium bisulfite, and that is going to remove any of the iodine. All right, and so this is something that they use in purifying water to get the chlorine out. It is a good reaction. We're not gonna, it's just a cleaning, so we're not gonna do the reaction mechanism for it, but it is a great mechanism for taking halides out of water, and that is the sodium bisulfite. So we are gonna add 3 mils of that. Pour that in there. That's going to get rid of any of the free iodine. So iodine was a catalyst. All right, and so we don't want the catalyst showing up in our product, making our product less pure. And so all right, so that is to get rid of any of the free iodine, the 20% sodium bisulfite. All right, so shake it completely and rinse the reaction with the acid mixture to remove material that adheres to the walls. All right, so we didn't really do that again. We should have. I should have added that to here. All right, so separate, wash it with 10 mil portions of 10% sulfuric acid. So we need our 10% sulfuric acid. All right, good. It's here. All right, I'm going to put our 10% sulfuric acid well, more 10% sulfuric acid. All right. So I'm kind of waiting for my magnesium to stop reacting before I put it into the separatory funnel. All right, so we're going to separate the ether layer. All right, and so ether has a density of 0.8-ish. All right, so the ether layer is on top and the water layer is on bottom. All right, so our triphenylmethanol has 6 benzene, benzene has 6 carbons. We have 3 of these 6 carbon benzene rings. So we have 18 carbons plus the carbon that the 3 are connected to. We have 19 carbons. All right, even though it has an OH, the 19 carbons dominate the polarity, and this is a relatively nonpolar molecule. It is polar, but it's relatively nonpolar. For alcohols, it's relatively nonpolar. And so the product is in the ether layer. It is not in the aqueous layer. All right, and so because of the large number of carbon atoms, it is going to act more like an organic compound than it will as a alcohol. So if you had like ethanol or isopropyl alcohol, those are very soluble in water. They only have 2 or 3 carbons, depending which ones you're looking at. And now this one has 19 carbons, and now it is not soluble in water. It is soluble in the ether layer. All right, the reaction here is still going. I probably shouldn't have put all the unreacted magnesium in there because it is taking a while to react that to completion. So I don't want that hindering our separation. If we want the 2 layers to separate, and then you take the layer off. If you got reactions going and bubbles going, that doesn't work very well for a separation. So we need to wait for this to stop. And so I'm stirring it to make the reaction go faster. All right, so if you got magnesium for the limiting reagent, that is probably the wrong answer, because that would mean that we were out of the magnesium. We are definitely not out of the magnesium when we are done. It is reacting with the acid. All right, now it's getting to be pretty close to done. Still a little bit. Again, swirl it up some more. Could maybe add a little more acid, make sure it's got plenty of acid in there to react at all. So you can see the 2 layers. The reaction is occurring in the aqueous layer on bottom, and it is producing gas, which is pushing that cloudy aqueous layer up into your clear organic layer. It's sort of like a lava lamp. You got the big hunks of things going up and then falling back down because it is getting some buoyancy from all the gas being produced, and it's getting pushed to the top, and then it's like, I'm a higher density than you, and goes back down to the layer it's supposed to be in. All right, and so swirling is going to make the reaction go much faster. That reaction was occurring in one spot. If I can spread it out to a bunch of spots, surface area is going to increase this reaction rate and get this reaction to stop anytime soon here. All right, it's still going. All right, so the reaction has slowed down quite a bit. I think we can go ahead and put that in our separatory funnel. We put the lid on our separatory funnel. With this gas is being produced, it is going to pop that thing right off the top. So a lot of reasons why you don't want a reaction going in a separatory funnel. So So again, you got to make sure our stopcock is closed. And the capacity of that is 125. This is going to be pretty close to capacity for that. Oh, look at that. Oh, it's still going. I thought it stopped. Alright, so the reaction has slowed down quite a bit. I think it's at a manageable amount. So we're going to go ahead and put that in our separatory funnel. Stopcock is closed. We'll see if this even fits it. Alright, and so since I swirled this so many times, I don't need to seal this off and rock it back and forth. All I'm going to do is I'm going to wait for the two layers to separate. And again, I want the ether layer. It is where the product is at. I should put the lid on for moving it. Don't spill. Okay. Alright, and so I'm just going to put this into here. So all of the washings are going to be the bottom layer, which is nice. If you want to keep the bottom layer, then you got to transfer it back into the top. After you pour that out, you got to pour that in. Here it's just we separate the two liquids and then we put in the next thing to do the washing with. Alright, so again, I'm not going to mix it because I've swirled it many times and the reaction was going for a long time. So all I'm going to do is I'm going to take out the bottom layer, which is the aqueous layer. And again, stopcock has to be off whenever you are opening. When you open the stopcock, you have to have the lid off, or it will not flow. So all the magnesium is gone. There's zero reaction going. It took a while, but all right, so now we're going to wash it. I got my papers all wet. All right. Okay. 10 mils of saturated sodium chloride. All right, so saturated sodium chloride, you should see sodium chloride on the bottom. There is a little bit but I have a giant bottle of the saturated sodium chloride, and then I take the top layer off of that, and so my saturated sodium chloride has very little solid on the bottom. Alright, so 10 mils of this, and that also keeps people from shaking it up and having solid sodium chloride into their flask. So you want, when you're adding the saturated sodium chloride, you want it to be the liquid and not solid floating in there. And so another reason to keep that. So when I add this in, you should see it going to the bottom. All right, so saturated sodium chloride has a higher density than your ether, so you see that it is going right through the ether layer and right to the bottom, and now it's being added, and you can see this clear, colorless. So you got your clear, colorless, saturated sodium chloride level. All right, so now we haven't mixed this up. I wasn't swirling it forever. So we need to find our stopcock, and then we need to mix this in. So we should probably get a little bit of stopcock grease. Ether will dissolve your stopcock grease, and so you want to have a little bit on there. You don't want very much. You don't want, because you don't want to have a whole bunch of stopcock grease in your product. And so you just want to use a very small amount, but you don't want this to get frozen shut. All right, so put that on, tilt it up. So a little bit of a pressure release. A little bit. All right, so then we can. All right, so it is nice and mixed up. So we washed with our sodium chloride. We let that separate. Doesn't take very long for that to separate. All right, so that was our saturated sodium chloride. All right, sodium bicarbonate. So 10 mils sodium bicarbonate. Our sodium bicarbonate is frozen onto the lid here. I need to find a way to get that off. All right, so the lid on the sodium bicarbonate. Where's the sodium? Let's see if we have another bottle. So the lid is on there very tight. So I found another bottle of sodium bicarbonate, 10 mils of that. that. Not too much pressure release there. Okay. All right, so this is mixed good. We can then separate that. All right, then one more time with our saturated sodium chloride. Finally with saturated sodium chloride. All right, 10 mils saturated sodium chloride. Right. Separate. So the sodium carbonate that was our last wash is reacting with the acid, the sulfuric acid down here, and producing some CO2. All right, so now we're going to dry it. So again, remember, drying it means we're going to take the water out. All right, so dry the ether solution over 2 grams of anhydrous magnesium sulfate. And then after that, we're going to distill it. All right, so 2 grams of magnesium sulfate. Magnesium sulfate. It is right here. 2 grams magnesium sulfate. All right, I'm going to put that in beaker. All right, I'm using a 15 ml beaker. again, the magnesium sulfate anhydrous is going to take any water out of our ether. So ether does have water solubility, and so we want to make sure that we're getting the water out of the ether. And to get the ether out, we're going to just pour it out the top. I'm going to wipe the top off to remove any stopcock grease that might be up there. And pour it in. Again, you're not going to see anything happen. If you see something happen, then that was really wet. So if it clumps up immediately, then you know that you didn't separate the water out very well. You had a lot of water in there. All right, so you don't see anything going on in here. It's just taking any of the water that's in the ether and removing it. All right, so now we're going to set up for a distillation. And this is going to be a strange distillation because we are keeping the stuff that we're heating. We're not keeping the stuff that we are collecting. So this is going to be a different type of distillation. All right. So let's get that ice bath. We'll use the ice bath again. Just we don't want a bunch of ether vapors in the room. So if I fall asleep, then you'll know that there's lots of ether vapors in the room. Right. So keep it relatively cold. And the amount of volume we have is right about 40 or so mils, so we can use our 100 ml flask for our distillation. And we will use our 25 ml flask. You got 40 mils, you might need more than 25, but yeah, let's do the 50. All right, and then we'll have the collection flask be the 50. Organic one, Grignard is the longest experiment. It might be the longest experiment for one or two. All right. So I'm going to get some more ice water for that. That'll keep that nice and cold, keep the ether from evaporating into the air. side, and then we have the thermometer adapter. Okay. All right, so we're ready to decant any water that was in here. Has now been sucked in by the anhydrous, and so we are going to then decant, which means I'm going to pour all of this ether with our product making sure I don't get any solid coming over. I want all the liquid, no solid. All right. All right, put in the thermometer. We're not going to need to monitor the temperature because it's just going to be the ether, but all right. So then we're just going to boil off the ether. Again, this is ether, so we shouldn't use a flame, except, well, what I'm going to be certain of is that I have all my clamps in place, and they are tight. All my joints are sealed. I have my condenser running properly. All right, all my ether has been put away except for what I have here. So I know where my ether is at. I don't have anybody across the bench from me with ether, and so it is safe to use a flame for this distillation. All right, can we see our distillation? Yeah, I think so. Okay. All right, so again, it's not going to take very much heat. We are boiling ether, so I'm going to turn this down. So it's not going to take very long for this to start boiling. And again, we are not, the product is not ether. We're just boiling ether off, and this is how we're going to do it. You can do this in the hood. Could just put it in a beaker, put it on the hot plate, and just evaporate it. But I am collecting ether. We're going to keep the ether to do other extractions or whatever. This is pure ether that we are collecting over here. So there's definitely a shortcut to this, and that is just to boil it in the hood. But again, you don't really want ether everywhere. Although you can buy it in the store as starting fluid for whatever, lawnmowers, motorcycles, whatever you need to start that won't start. All right, so the boiling point, let's see, yep, it's coming. All right, so looks like I was pretty close to the boiling point. Here it says 36. I said 38 or 39. Anyway, here we're boiling this at 36 degrees Celsius. All right, and it's dripping. You can see it dripping in over here. It's not dripping in too fast. It's going at a nice rate. And you can see the water is going through our condenser, cooling that off. And it's a nice boil. You're not boiling it like crazy. And again, our product is over here. We don't want to heat it very much. We don't want to end up charring our product. Alright, so after we get done with this, what is the next step? Alright, so we're going to distill off the ether. Then we're going to stir the residue with petroleum ether or Grignard, about 5 mils per gram, and collect the solid on suction filtration. Alright, so I'm just going to look at it and probably estimate it to probably be about a gram or two. So probably 5 to 10 mils of Grignard. So I will get that ready. While that is still coming over, yep, good, nice dripping over there. Another direction of the cylinder. All right, so we're going to use petroleum ether. Nice giant bottle of petroleum ether. I'm going to come do that over here, way far away from the flame. And get 10 mils of this. Alright, so I have that prepared over there for the next step. And it's still going. So at some point when the volume gets low enough, then you're going to have a solubility issue and you're going to start to see some product precipitate out of the ether. So right now all of the product is soluble in this ether. Now once we remove a bunch of the ether, then you don't have the solvent to dissolve the solute, and so the solute will start to precipitate out. Boiling point is still at. Yeah, it went up a little bit. It's up at a little above 40. Still a little bit above 40, still dripping in, yep, still dripping over nicely. Bring it a little closer. All right, so you got your good boil there for your yellow solution, and then it's coming out here at a nice rate, and then you can see it dripping into this flask. All right, so that is a very good rate. That is, you don't really want it any faster. Of course, you don't want it slower. You'll be here all day, but so that is a good rate of distilling. I'll get the 43, 44. So when the drips slow down, I increase the heat. And once the temperature gets above 50, then I will stop heat. So it's going pretty quick now. All right, so now our solution over here is getting very cloudy. The temperature is going up. We're above 50 now. All right, which indicates to me that any ether that was in there is now gone. Once we hit the 50-degree mark, any ether should have been taken over to the top, or to the other side. So, wait for it to get up there. Okay. All right, so I'm going to kill this. All right, so now I'm going to add the petroleum ether. All right, so Pyrex, you can go from boiling to ice water, and it will not break. The glass. You try that with household glassware, it will crack immediately. So it's cloudy. Looks like a little bit of precipitate in there, so I'm going to cool this down in this ice bath. Alright, so then I'm going to add my petroleum ether, and then I'm going to filter it. Alright, so when I added petroleum ether, you have the yellow solid formed, and that is the triphenylmethanol. That is the product. And so now all we have to do is to do a suction filtration and then weigh that product. So that is quite a bit of product at the bottom there. So this is going to be a pretty good yield, and looks to be a nice yellow, not an orange color, so it looks quite pure as well. Alright, so let me aim that over here so we can see what I'm doing. Wait, the best part of just watching and not doing is when I'm done, I can clean it all up, and I guess you gotta bright it all up. Alright, so I didn't name it over there, did I? Okay. Alright, so we have our Grignard funnel with the filter in there. Okay, and then we turn on the water aspirator. As the water goes down, it pulls the air in through here. Alright, so this is a suction filtration. Alright, so initially I want the liquid to hit the paper and form a seal. I don't want any of the solid to go around the sides. So the liquid has to form a seal before I add any of solid. Alright, so that looks good. Alright, so now I got to get all that solid out of there. Alright. Wow, that is a pure solid. Usually it's a yellow. This one is white. Alright, and I got some more petroleum ether to get the rest of the solid out. And probably another shot of petroleum ether, and then all right, and the last shot of petroleum ether. All right, that looks great. All right, so let's see. We have to get a mass. We also have to get a melting point. Okay, so. Alright, so I'm going to get the Digimelt ready. Okay, take the melting point. Okay, so press start temp. Start temp. We're going to go 150. Okay. Press to exit. Okay, and then we're going to repeat for stop temp. Stop temp. Okay. And then press start stop. All right, so the suction filtration it is continually blowing air over our solid, drying it so that we have a mass of the dry product. I'm getting the capillaries ready to take a melting point. Once we have a mass and a melting point, we are done with the experiment. Okay. All right, so I had to seal off one end of the capillary tubes. That was what I did there. So that is ready. Okay, so now I'm going to put the product to there. All right, so that is the product. It is a white solid with a tint of yellow. Usually it's a lot more yellow, sometimes orange. So this is a very good looking product for the triphenylmethanol. So I'm going to get our product into again because oh yeah, good. All right, so I'm just getting the product from the Grignard funnel into the weigh boat so we can get a mass of our product. All right, so I got most of that. You're always going to lose some, so there's going to be some solid there. Okay. All right, and so now I'm going to get the mass of our product. So that is what our product looks like in the all right, so we got 1.4810 grams. 1.4810 grams. So 1.4810 grams. So that is a good amount. All right, now let's see what we get for our melting point. So we have our capillary. We're going to put some amount in our capillary, and we're going to tap it down. And so then our solid is at the bottom of this capillary. All right, we have this